Things are about to change in a big way. Scientists have never been so able to solve the deepest mysteries of nature, to solve the kinds of mysteries that have led over the last couple of centuries to some of the greatest achievements of humankind. And yet, just as we're poised to make some of our most profound discoveries, government investment in this kind of basic research is rapidly drying up. Basic research into the fundamental ways that nature works could one day end world hunger, halt global warming, help us understand the origins of our universe, and ensure our survival. One thing it will certainly do is dazzle us with the thrill of knowing at the most basic level who we are and what our world is made of. But funding for that kind of deep understanding of nature is in jeopardy. Somebody has to encourage basic research. Meet the Discovery Prize. Each year, Stony Brook University researchers submit proposals for a chance at the $200,000 Discovery Prize. Our goal is to encourage our faculty to ask the big questions and pursue the unknown.
We're trying to build a new kind of technology.
Can we utilize wireless energy?
So in one experiment, we can gain a wealth of knowledge.
Diversity is relevant for HIV treatment.
With the Discovery Prize, Stony Brook continues to invest in the research that advances our understanding of who we are and where we're going. The Discovery Prize, taking on the big ideas that change our world, only at Stony Brook University.
Please welcome the president of Stony Brook University, Dr. Richard L. McCormick.
Good afternoon, and welcome to the 2025 Stony Brook University Discovery Prize competition. The Discovery Prize was established in 2013 through a generous donation from the Stony Brook Foundation, and in the 12 years since, it has become one of our most cherished traditions. What makes this competition so special is its commitment to the untethered pursuit of scientific discovery and curiosity-driven knowledge free from commercial or political pressures. The Discovery Prize funds the kind of research that may be so revolutionary, so contrary to convention, that funding agencies are unlikely to provide support. Research that takes us by surprise and changes the future of our world. It also means to support the careers of rising stars on the Stony Brook faculty, visionary thinkers whose research pushes the boundaries of their fields and who require an institution like Stony Brook to recognize and support their aspirations. From tracking the chemistry of ultrafine aerosol particles to revolutionizing nanophotonics and promoting neurological recovery, the research of the past Discovery Prize winners exemplifies the inevitable curiosity that defines Stony Brook University. In a world that is rapidly evolving, often in unpredictable ways, we depend upon the dedication of researchers like the scholars we're celebrating today. We depend on their creative problem solving and their relentless pursuit of new knowledge. We depend on them to spark new solutions, forge unexpected outcomes, and ultimately transform our world. Jennifer Cano, Paolo Celli, and Ifan Joe, thank you for your courage and your tireless pursuit of knowledge. And congratulations for the honor of being this year's Discovery Prize finalists. We will have the privilege of hearing from Jennifer, Paolo, and Ifan in a moment. But first, I'd like to acknowledge the Marilyn Simons and David Spergel, president of the Simons Foundation, who, along with the late and beloved Jim Simons, have been the leading force behind the Science Philanthropy Alliance and the inspiration for Stony Brook's Discovery Prize. Their remarkable gift of $500 million in unrestricted endowment support will fuel additional research and discovery at Stony Brook, as well as student success and so much more for generations to come. We also extend our gratitude to the Stony Brook Foundation Board of Trustees, whose steadfast commitment to our research has enabled us to achieve so much, as well as the Stony Brook Council for their enduring partnership and leadership. Thank you also to our dedicated coaches from the Alan Alda Center for Communicating Science, who helped our finalists refine their presentations to articulate the full impact of their work. We thank as well our esteemed judges and review panel for their critical role in the evaluation process. In just a moment, we'll meet our Discovery Prize finalists, those very researchers whose work is so integral to our university's mission. Each of our judges received the finalists' written detailed proposals in advance, and today each finalist will present for 10 minutes, followed by a 5-minute Q&A. Then we'll have the honor of announcing this year's Discovery Prize winner. But first, I'm delighted to welcome to the stage Dr. Chris Johnson, Professor of Chemistry and winner of the 2023 Discovery Prize.
Thank you. What we have here is basically a summary of what we think we know about what's going on in the atmosphere right now and what humans are doing to change it. The big picture that you want to take away from this is this bar down here. So this is the total effect of total warming effect that humans are causing on the climate. And we all, we hear about CO2. This is the portion of it that's CO2. This is something that that everyone's worried about, and we're trying to figure out what to do about it. But what I really think a lot about is the uncertainty. That's this error bar here. And you can see that this error bar is really big. It's most of the effect. And the world is going to be really different in a few decades if the effect is actually down here at 2 watts per meter squared or way up here at 3.5 watts per meter squared. This could be the difference of several degrees of warming. And so understanding how to shrink these error bars is really the core of what my group is working on. And when we look at this, the other part of this plot that has big error bars is this so-called aerosols thing. Aerosols are particles in the atmosphere. They actually are thought to cool the atmosphere by essentially forming clouds or scattering light. And you can see that the uncertainty of the aerosol effects is almost as big as the entire effect. And so if you want to shrink these uncertainties, this is where your biggest bang for the buck is. And this is what we're working on. So why is it hard? So one thing that's hard, so we think particles in the atmosphere, okay, they're small, they're probably round, and almost none of these things are true. They're a huge range of sizes, they're a huge range of shapes, and more importantly, they're a huge range of different chemical compositions. And it turns out that the chemistry is really important to being able to shrink these error bars. And so, why is it hard? It's hard because we don't actually have very many good tools to probe the particles that are in the size range that actually matter for forming clouds. And so this range here. So what you're seeing here, this is essentially a plot of how many particles you're likely to find at various sizes. 1 nanometer is about the smallest particle you can get. 10 nanometers and 100, or 10 microns and 100 microns are sort of dust, things that you can actually start to see. For forming clouds, all the action happens somewhere between 10 nanometers and 1 micron. And it turns out that if you look at the tools that we have available to us, whether we're looking at particles that we collect on surfaces or whether we're looking at particles that we suck out of the atmosphere, there's a huge missing piece. And that missing piece is right at the beginning of when these particles start to form clouds. So we need a new instrument in order to really start to make measurements here that can inform models that shrink these error bars. That's what we're working on. So the Discovery Prize is allowing us to do the basic legwork to actually figure out how to make this instrument and then to construct it and start to do proof of concept demonstrations. So what this instrument is going to do is we're going to measure the size of particles, their chemical composition, and their propensity to form clouds simultaneously. And we have to do this one particle at a time. The reason we have to do it one particle at a time is because there's so many different types of particles out there. There are particles that come from dust, there's particles that come from plants, particles that come from animals, particles that form spontaneously in the sky, and they all do different things. And if you make a measurement on the average of all of them, then all you learn about is that particular average. What you don't know is then as soon as something changes, maybe the weather changes, maybe you move over land instead of over the sea, everything that you learned about that average is gone, and you're dealing with a completely new set of particles that's a completely new average. And so what we're going to do is basically measure these things one at a time, understand what their chemistry is, and understand how likely they are to form clouds. And the way we're going to do that, we're going to need to measure the mass first. This is already hard The mass is going to tell us the size. What we're going to do is basically almost like make a particle ping pong machine or a particle pong machine. You have a particle, you suck it into this size detector, and it essentially bounces back and forth between two mirrors. The bigger a particle it is, the slower it goes. And so if we can keep track of, basically it passing back and forth time by time, then we can figure out what its frequency is, and then we can figure out what its mass is. This is already a sort of a forefront challenge. There are a few instruments in the world that can do this. But we need to then measure chemistry. The way that we're going to measure chemistry is using something called vibrational spectroscopy, which is a technical term, but all it really means is that each one of these sort of like pairs of atoms in a molecule has a specific way that it vibrates, and that shows up at a specific place on a vibrational spectrum. And so this is one instrument that chemists use a lot. This is another instrument that, that chemists are starting to figure out how to use, and we're going to combine the two of them in order to figure out what's going on. And then eventually, we'll bleed some water into this thing and just see how fast its size changes as it turns into a cloud droplet. So things are going on. We've got the right person for the job. Casey Schultz joined my group around the same time as we got the Discovery Prize money. And so he's been working hard to simulate this thing. So we have a computer simulation that shows it's going to work, simulate its performance so that we can figure out that we can actually measure what we want to measure, and design all the parts and send them off to machine shops. So this is where we are now. We're awaiting, or well, we're receiving parts as we speak. This is going to be over the next couple of months assembled and then hopefully operational by the end of the summer. And so stay tuned. We hope to have some fun things to tell you about before too long. Thank you.
Thank you, Chris. That was an awesome presentation. Our judges this year share a passion for inquiry with our finalists. They represent the spirit of discovery that defines a truly transformational scholar. We are proud and honored to have them here with us today. Dr. Barry Barish has been a member of the National Academy of Sciences since 2002 and a member of the American Academy of Arts and Sciences since 2005. He served as a distinguished professor at UC Riverside and is the Ronald and Maxine Linde Professor Emeritus at Caltech. In 2017, he received the Nobel Prize in Physics for the first ever observation of ripples in the fabric of space-time predicted by Albert Einstein more than a century before. Dr. Barish currently serves as the President's Distinguished Endowed Chair in Physics here at Stony Brook. Dr. Joanne Hewitt is the director of the U.S. Department of Energy's Brookhaven National Laboratory, where she oversees a team of more than 2,800 scientists, engineers, technicians, and professionals, and is president of the Brookhaven Science Associates. She's also a professor in Stony Brook's Department of Physics and Astronomy and at R.C.N. Yang Institute for Theoretical Physics. Dr. Hewitt is a fellow of the American Association for the Advancement of Science and the American Physical Society. As a theoretical physicist, her research probes the fundamental nature of space, matter, and energy. She is best known for her work on physics beyond the standard model of particle physics. Dr. Shandi Sandvik, Senior Vice Chancellor for Research, Innovation, and Economic Development at the SUNY System Administration, and Professor of Nanoscale Engineering at the State University of New York Polytechnic Institute. Her research is centered on the physics and technology of photonic and electronic devices for lighting, power conversion, and senses. Dr. Sandvik was appointed as the first presidential fellow with the Research Foundation for SUNY in 2013, SUNY Provost Fellow in 2012, and was recognized as the New York Governor's 2005 Woman of Excellence for her professional accomplishment and contribution to the community. Let's have a round of applause for our distinguished judges. Now, I'm excited to introduce our first finalist for the Discovery Prize, Dr. Jennifer Cano. Dr. Cano joined Stony Brook University in 2018 as an assistant professor in the Department of Physics and Astronomy, and she currently holds a visiting scholar appointment at the Flatiron Institute in New York. Her research is in the field of condensed matter theory, delving into fundamental principles such as classification and predicting new material platforms to realize exotic quantum phases. She developed the theory of topological quantum chemistry, which combines group theory, topology, and chemistry to predict new topological materials. The title of her presentation is Theoretical Framework for the Discovery of Topological Moire Materials. Please welcome Dr. Cano.
Probably most of you have one of these in your pocket. But have you ever thought about how much energy it consumes? In fact, phones, computers, and the networks that power them make up 10% of global energy consumption. That is a lot of energy. It's on par with the airline industry. Thus, it is imperative that we develop energy-efficient materials to power our devices. So where is all this energy going? Well, when electrons travel through wires, they bump up against each other, and they bump up against the walls of the wire. And all of those collisions cause heat, which is wasted energy. We call it dissipation. You can think of this like when you're traveling in heavy traffic. Even though everyone wants to move in the same direction, there's still collisions, and those collisions waste time and energy. This should be contrasted to the Autobahn, which is the German highway system known for highly efficient transport. What we need is an Autobahn for electrons. But is a dissipationless wire even possible? Well, we know one place where it exists, and that's a superconductor. But superconductors have a different problem. They only operate at very, very low temperatures. And so that doesn't help us. We need a new solution. The solution that I propose is a phase of matter that occurs when you put a thin slab of material in a large magnetic field. When this happens, the electrons in the material feel a force from the magnetic field, and that makes them want to move in circles. And when the magnetic field is very large, it actually forces the electrons to move without any collisions, thereby creating a perfectly conducting wire, a dissipationless wire on the edge of this material. This is an amazing effect. It's called the quantum Hall effect, and it was the subject of 2 Nobel Prizes. So with this perfectly conducting wire, does it solve our energy problem? Not quite, because it requires this large magnetic field. This is the sort of magnetic field that is so large, it will ruin your credit cards, it will break your pacemaker. It's not the sort of magnetic field that you want in your pocket. So this begs the question, can we separate these ingredients? Can we have our quantum Hall effect without the large magnetic field? This question was answered in a seminal 1988 paper. And there it was shown that theoretically, yes, the quantum Hall effect can exist without a magnetic field. But the author of that paper did not know any materials that would realize this phenomenon. And so for the next 25 years, scientists have been trying to find materials that can realize the quantum Hall effect without a magnetic field. And during that time, there have been many breakthroughs, but I'm going to propose a different approach. I'm going to propose that instead of looking for materials that realize this phenomenon, we build them from the bottom up. And since the quantum Hall effect requires a thin slab of material, our building blocks are going to be the thinnest possible materials that are just 1 atom thick. We call these 2-dimensional materials because electrons can move sideways or front backwards, but they can't move in the 3rd dimension. So do 2-dimensional materials exist? Yes, they do. The most famous of these is called graphene. Graphene is made of carbon atoms, which are arranged in the honeycomb lattice that you can see here. When graphene is stacked in its 3-dimensional form, it forms graphite, which is the common ingredient in pencil lead. But in its 2-dimensional form, graphene has amazing electronic and structural properties. It is extremely strong and extremely flexible, so much so that if you made a hammock out of graphene, it could support the weight of a cat, even though it's thinner than a spider's web. This is an amazing material, which was the subject of another Nobel Prize in 2010. And the discovery of graphene launched the whole field of two-dimensional materials. And now there's not just one or two or three of these materials. In fact, a recent database predicts that there's over 6,000 two-dimensional materials. This is a huge playground for us to find our perfect conductor. Two-dimensional materials also afford us another possibility, which is we can stack them to make new materials whose properties we can tune by design. This materials by design principle has often been compared to playing with Legos, because with a few simple ingredients, there's so much that we can build. But there's one thing that we can do with our two-dimensional materials that we can't do with Legos. Legos have to be stacked aligned with each other. But two-dimensional materials can be stacked with a twist angle. See what happens when you change this twist angle. As the twist angle is varied, you see an interference pattern. And that interference pattern dramatically changes size. That interference pattern that you can see with your eye, electrons also see that interference pattern. And so as the twist angle is varied, it can dramatically change the electronic properties of a material. In 2018, it was shown that if you stack two layers of graphene and you change their twist angle from just 0 to 1 degree, it can change, that material can change from being a metal to an insulator to a superconductor. And the following year, it was also shown that that same material could realize this quantum Hall effect without a magnetic field. So this was an amazing breakthrough. But it's plagued with its own problem, which is that it also is limited to low temperatures. And so this makes us wonder, with all of these 2D materials and all the ways that we can stack them and twist them, there must be somewhere in this large phase space where we can find this effect at a higher temperature. The problem now is that we don't know where to look. So what we need is an instruction manual. And this is where my work comes in. So I'm a theoretical physicist. So what I want to do is predict the properties of materials computationally. The problem with these twisted bilayers is that they're so complicated. Their repeating unit from this interference pattern contains so many atoms that we don't have the computational power to run the algorithms that we would like to run. So we need a new approach. And that new approach takes the form of an algorithm that my team published earlier this year. So our algorithm has 3 simpler ingredients. The first ingredient is the electron wave function in one layer. That tells us how electrons behave when they move around in just one two-dimensional material. And this is something that's easy for us to compute because it just involves that single layer. The second ingredient is how electrons tunnel from one layer to the next. And this is also easy for us to compute because we don't require that those 2 layers be twisted. And finally, the third ingredient is the size and orientation of that interference pattern. And this is what allows us to interpolate, to take our results from our first 2 ingredients and turn them into properties of our twisted bilayer. So with these 3 ingredients, our algorithm can efficiently predict the properties of our two-dimensional twisted materials and efficiently predict whether we'll realize a perfect conductor. So we've tested this on a couple of examples, but what we want to do next is to interface this algorithm with the database of thousands of 2D materials. The result will be many new predicted perfect conductors. This will serve as our instruction manual. We will hand over our predictions to our experimental colleagues who can validate them in the lab. And in the worst case scenario, they don't find any material that performs better than twisted bilayer graphene. But the dream is that they will find one or more materials that will realize this quantum Hall effect in zero magnetic field at room temperature. This discovery would dramatically transform modern technology. And it's this material that would serve as our Autobahn for electrons. And this material will be the backbone of the next generation of energy-efficient electronics. Thank you.
Thank you. This was amazing. You answered one of the questions that I had, and that was how do you, being a theorist, how do you tie it back to experiments? And then how do you take what experiment in reality, that's the reality, right? And then put that back into the algorithm. So you responded that the experimentalists will take that, and then
we need them to validate our results. Theory is not perfect.
Yeah, exactly. So kind of connected to that. But differently, as your algorithm, as I understand it, it's for perfect 2D material. And as we know, 2D materials, they do have defects. And they are in an environment, and there's all of that. So how do you then take that approximation, knowing that, again, you're simulating perfect material, and materials are not perfect?
Yeah, so I would say that, well, a couple of things. As a first go, we want to know whether this can exist in the perfect material, because if it can't exist in the perfect material, it probably also can't exist in the imperfect material. So this is kind of our starting point. And then I think once we have that prediction, then we would want to go back and figure out, once we have these candidates, if what we predict in theory is not observed in the experiment, then we need to figure out why. And so there's a couple of options, and basically what we would want to know is what if defects are the problem, what is the type of defect? Is it actually a replacement of an atom? Is it buckling or strain, some kind of structural defect? And I think depending on what those answers are, then we would need to go back and refine, because we can actually refine the data in those inputs to include certain types of imperfections. But I think our approach would be, first, we want to make a prediction for the perfect material, and then that would be like the next iteration. Once we have targeted candidates, we can study them in much more detail. This is meant to be a framework to do like a high throughput search.
Yeah,
Thank you.
Thank you.
Okay, I'll go next. A question mainly from your proposal. This was a very nice presentation. Thank you very much. So the foundation of this work is based on an algorithm that you discovered, which basically applied perturbation theory to the electronic structure of the moire materials, right? So what gives you confidence that this particular perturbative expansion is valid?
That's a great question. Yeah, so one reason that I have confidence is because we tested it on two different models. One of those models is the graphene model, where this was already observed. And the other is in a different class of materials called transition metal dichalcogenides. So we have confidence that it applies in those two examples. Another reason that I have confidence is because we're talking about stacked materials, we're perturbing in the couplings between them, and that's intrinsically a lot weaker than coupling in a single layer. So it makes sense. Perturbation theory is something that makes sense in this context. But it's certainly not a guarantee, and so that's one of the things where, again, I would say that there's a big need to validate the theoretical results. But given the huge space that we're talking about, I think there's also a need to make a theoretical starting point.
Yeah, I wonder, again, from the proposal and not the presentation, you divide the work into 3 stages that presumably will converge to the final solution. Yeah. Can you very briefly say why these 3 stages and what confidence you have?
Yes, right. Yeah. So there's 3 stages in the proposal, which I didn't mention here. Right. So in the first stage, we first want to figure out, the first is basically just a scan for materials that are going to be that are going to be kind of candidates, basically. So this is basically what are the 2D materials that we can put into our twisted heterostructures. That's, yeah, maybe I should say something like, if you have a metal which has a lot of electrons at the Fermi surface, it's too complicated. Our perturbation theory will break down, so we don't even want to waste time on those. So we throw those out. So we're left with semiconductors, basically. That's step one. The next step is that I talked in this talk about the twisted bilayers, but there is kind of an easier solution, which is that instead of making twisted bilayers, you can engineer, like nanofab, spatially modulated periodic potential. And this is actually an experiment that's already been starting to take place at Stony Brook. There's one paper, joint theory experiment paper that my group is involved in. And so in that way, what we're doing is we don't have the interference pattern, but we're creating a large superlattice. So this is a little bit easier because we only have one layer. We don't have two layers to begin with. And so that I have a lot of confidence that our approach is the right one, because the strength of that potential can be tuned in the lab. Like there's kind of a knob to tune the gate voltages. So that I have a lot of confidence will work, and we've already used that to predict properties of bilayer graphene with a modulated potential. The twisted part with involving two layers is kind of the big leap. And so like I said, we've tested this on a couple of models, but there's a lot of material infrastructure that we need to develop to do a high throughput search on this whole database. And so that's kind of what the actual proposed work would be on.
Thanks.
Thank you, Jennifer, for that presentation and those eloquent responses to the questions. Our next finalist, Dr. Palo Chelli, joined Stony Brook University in January 2020. Dr. Chelli specializes in solid and structural mechanics, structural dynamics, and wave physics. Her research group uses precision desktop experiments, in-house fabrication, numerical simulations, and theoretical derivations to explore the mechanics of adaptive structural systems. His work focuses on shape-morphing structures, dynamic structures with evolving properties, civil engineering, robotics, and renewable energy structures. The presentation today is entitled Load-Bearing Enviromorphing Structures. Please welcome Dr. Chelli.
Thank you so much for the introduction, and thank you all for being here today, and thank you for the opportunity. When you think of structures, probably this is what you have in mind. A building frame made of wood and concrete. A bridge made of stone and metals. If you're really a broad thinker, you may also think of structures beyond civil engineering. The International Space Station, a space structure made of polymers and metals, or a metallic bone implant there at the bottom. These are structures as you know them. And structures as you know them are typically static and unchanging. Yet, over the past few decades, researchers in my field have tried to show the utility of flexibility. Essentially that allowing structures to change can be used for functional purposes. This is the reason why, in my research group, we do research on shape-morphing structures. There are structures that are specifically and carefully designed with careful geometrical arrangements of parts such that they can morph between drastically different configurations. You should not be completely new to the idea of morphing structures. In fact, many toys are morphing structures themselves. What you see there on the left is a Hoberman sphere. Something that can morph between a small spherical shape to a much larger spherical shape. What's on the right is something that if you have small kids, you probably have at least one of those in your house. That's a Pop-It fidget toy. Turns out there's much more to that toy than you may think. In fact, each one of those domes is a carefully crafted morphing structure that possesses two stable states, the upward dome and the inverted dome. And you can snap between them at will. In my group, we try to do research on morphing structures that are not just mere toys. Okay? Let's say that you want to create a structure similar to this one. This is called a grid shell, and it's a canopy structure that can cover a large area. Okay? You can see in this image that to erect a structure like this, you may need cranes, and that to keep the structure in that shape, you probably have to anchor it at many points at these boundaries. In my research, we came up with a concept for a similar structure that is made of a careful arrangement of geometrically tailored units, such that when you actuate it at 2 points, it pops into a dome shape. And then through boundary pinning, you can have it keep its morphed state. And therefore, there you have it, a dome that can be easily transported in different locations. Here is another example. In the United States, all utility lines, most utility lines are above ground. And this poses problems and challenges. So in my research group, together with a team of roboticists and geotechnical engineers, we're trying to come up with a robot that can dig underground, move like an earthworm, and as it does this, deposit a conduit with utility lines inside. So to avoid costly above ground operations. At the core of this robot, there is a morphing structure that needs to interact with the surrounding soil in order to allow this robot to propel itself. One of the issues with morphing structures is actuation. Here is an example of what I mean with this. Let's say that you want to transform something flat into an arch. You can do that by compressing it at its boundary points, as you see over here. Once you release the actuation, the structure goes back to its original configuration. Now, in my lab, we came up with this concept of a structure that is very similar, but it has those additional arches in each one of the 3 units. And each one of those units is very much like a puppet toy. It has a first stable state on the left. Once you snap it, it assumes a second stable state on the right. And you can say that the stable state on the right has a curved base. Once you put many of those units together, as you can see up there, you can go from something that is initially flat to an arch. And that arch is capable of retaining its shape. And you can also use it to support loads. Here, I have a larger scale version of this unit made of a structural material, wood. And you can see that to try to make it morph into the second stable state, it takes quite a bit of work. It's not a natural motion. And this is to show you that actuation is a problem, okay? Especially if you want to make these structures at a large scale. However, I think we have an ace up our sleeve, and that's environmental actuation. In fact, every single material wants to expand and contract due to changes in environmental conditions, which could be humidity or temperature. Typically, this is seen as something to avoid. Okay? Here, thermal expansion of these metallic railroad tracks is what caused them to buckle and deform and making this railroad unusable. Yet nature uses these changes for function. What you see here is a pine cone, and each one of the scales of a pine cone is made of a careful arrangement of different layers of wood, such that when humidity increases, those scales bend and they release seeds. Here is an example of a similar structure from my research, where we built a structure made of titanium and aluminum, some of the strongest metals you can think of, through a very careful geometrical arrangement, such that due to a change in temperature, this could almost double its height. This leads me to my Discovery Prize idea. What I would like to do is to understand how to realize structures that have an initial shape under some certain environmental conditions. And when the environmental conditions change, let's say it rains and humidity increases, or you could do this artificially with a hose, if you may. The structure morphs into a second, drastically different shape. And it's able to retain that shape even when the environmental conditions go back to the original one, and the structure is able to carry loads, even under different environmental conditions. How do I plan to do this? Well, there are 3 pillars to the research I plan to do. The first is fabrication. We need to understand how to put together materials with different characteristics and different expansion with respect to humidity and temperature in order to create some fundamental building blocks Let's say a bilayer that can morph from flat to a curve. Then we need to understand how to put this together into some structural forms that allow us to achieve our goal of creating something that is flexible enough to morph, yet strong enough to carry loads. And this we will do through models and experiments, and this is a bit the signature of my lab. And finally, large-scale demonstrations. We would like to create one of the structures and to maybe showcase it to the campus community if everything goes well. I see many of you may be thinking, so what? Why am I even thinking about this? Well, as a person that loves fundamental research, I'm just thrilled about the idea of creating something that nobody has done before. Yet, this doesn't stop me from thinking about some potential applications of these structures. Think about building envelopes that can adapt themselves to different environmental conditions, for example, to different wind loads, as to make the building more aerodynamic in certain conditions and to reduce vibrations of that building. Think about adaptive, self-deploying coastal barriers that can sense a change in water level and can self-deploy themselves to protect a coastal community from incoming waves. If you really want to think far, think about self-building habitats for the moon or other planets. Why the moon or other planets? Because in other planets, especially the moon, environmental swings in environmental conditions are much more dramatic. On the moon, the temperature swings between of several hundred degrees. And you cannot bring a construction crew to the moon, but you could bring one of the structure, assemble it there, and have it self-morph into a dome shape that could be the skeleton of a habitat. If you really want to think small, think of capsules for targeted drug delivery. Okay? You could build small capsules that when they reach a specific part of the body, where there are specific temperature or humidity conditions, delivers a drug payload. And there are probably many other applications that I have not thought about. Why would getting this Discovery Prize really matter to me? I started thinking about this idea of enviromorphing structures in the summer of 2020 with the very first student that joined my research group, Sujata, who is also here today. She was a high school student at the time. Fortunately, she had a sauna in her basement, which is an environmentally controlled room where we could basically investigate the basic bending of wood by layers. And this convinced me that pursuing research in this direction was something worth it. If I were to get this prize, we could finally continue our research together with the proper equipment. With that, I would like to conclude and thank my team members for their patience, my sponsors, my department for the continued support, and I would be super happy to answer any question you may have. Thank you.
Great presentation. I really have a very curious question here. So you have this structure, and it changes its shape due to the environment that activates it. When the environment changes back, how come it stays in its shape?
I think there are two ways to make that happen. Through what I like to say, energetic barriers or physical barriers. So a structure like this one, the one you have seen here, has an energetic barrier. If you think about the potential energy of the structure, it has two minima. This is one minimum, and the second state is the other minimum. I can engineer this minima, I can engineer the barrier between them, and I could make it so that the second minimum is lower than the first minimum, such that this has trouble going back to the original configuration. This probably needs to be done by endowing the structure with some pre-stress at the beginning, so the fabrication will have to be tailored, but I think this is doable. The second way is through physical barriers, meaning that you can really create structures that when they morph, for example, they have a ratcheting mechanism or something that impedes them physically from going back to the original configuration. Those are my two ideas. Thank you.
That's good to hear. If I were on the moon, I wouldn't want my structure to collapse on me.
Hopefully not.
My questions may be a little naive, but we usually think of building structures that are immune to try to make it immune to the environment. And you're breaking that rule and trying to make structures that react to a particular thing in the environment. But there's many parameters in the environment. There's many different things, not just temperature, humidity, wind, I don't know. How do you isolate really on just the parameter that you have in this demonstration?
So
or is it a kind of, I don't know.
No, it's a great question. And I think that at this stage, I have to identify applications where applications/materials/structural forms such that only one of these plays a role or plays a major role. That said, there is much more to be investigated about this type of structures if we were actually to make them. Their durability. When they're subjected to further environmental cycles, they're loaded. So can they carry those loads? But this is just the beginning of trying to get in that direction, which, as you said, is something that is kind of like not present out there today. So just a small step, and then there are so many. I'm going to be opening a can of worms, in other words. Thank you.
That's what I was asking.
Yes, it's a can of worms.
So Barry stole my question.
Ah.
That was exactly my question, that in the environment, in this real world, there are multiple variables. And one assumption that, as I was reading your proposal and listening to you, that you make is that the strength of one variable is more important than the interaction between variables. So that is not being taken into account. And I wonder if by not considering that interaction between variables, so it could be that the single variable itself is not as important, but the interaction is very important. By not taking that into account, whether what it would do and whether computation may be the way to actually take that complexity into account.
Yeah, so, okay, this is why my research is not just about experiments. At the same time, I need to come up with structural forms, and I need to make sure that I can make them. Otherwise, I'm the type of person that I cannot just trust my models. Okay, I need to make something, and I need to verify it. But at the same time, you have the right point there, which is through computations, by building models of these structures and really understanding how these structures respond, maybe not just to one stimulus, but multiple stimuli, if that is going to change things. I would definitely do that. Plus, I also think that we might be able to leverage different stimuli for function, meaning that we could use one stimulus to produce one small change, and then another stimulus to produce the change we want. So we can maybe introduce also some basic computational capacity in these structures.
Yeah, absolutely. If I could maybe just continue with just very brief, this is probably very brief to respond to, I assume. So biomimicry has been around for a long, long time, and I wonder what your thoughts are around why people haven't done this already.
So the people have made structures that are capable of extreme bending, but they've not made structures that are capable of extreme deformations and that they can retain their shape. And I believe that the reason is because we've only started to concentrate. People have been around these morphing systems for a while, but only a few try to understand how to upscale these morphing systems to scales that are of structural interests. I think I'm one of the few that does that. And for that reason, I just don't think people were thinking that morphing structures would be useful at all for structural purposes. Maybe they're not, but hopefully they are for some of this.
Thank you.
Thank you so much. Thank you all. Thanks. Thank you.
Thank you, Pello. Dr. Yvonne Zhou became an assistant professor in 2022 after serving as a postdoctoral research in the Department of Electrical Computer Engineering at Stony Brook. Dr. Zhou works at the intersection of power systems, quantum computing, and machine learning. She and her students are developing intelligent, adaptive, and ultra-scalable power system operations to advance a resilient energy sector. Her research focuses on designing AI and quantum solutions for real-time analysis and decision-making in ultra-scale power systems with massive distributed resources. She'll be presenting today on revolutionizing power grid computing through quantum-driven analytics. Please welcome Dr. Zhou.
you for the introduction, and thanks everyone for being here today. Now, let us just take a moment to think about what might be the largest human-made system on this planet. So you probably have the answer in mind because I'm here today to introduce the power systems. But really, power grids are among one of the largest and most complicated dynamical systems that is ever made by the human society. Taking the US grid as an example, our current grids already have tens of thousands of generators and millions of distribution transformers. And within decades, we will further have over 100 million distributed devices and doubled power load. What makes things even more complex is that we are seeing the increasing frequency of faults, attacks, extreme events, and power system will require real-time control to survive those numerous events. So all those factors just mean our already very large and complicated power system are just becoming even larger and more complex. And to successfully handle such a super complicated system with millions of devices and numerous events, a critical aspect is really to have very powerful and scalable computational technology to study the system behavior and to make operation decisions. For decades, we have been relying on the classical computing to perform calculation, like the classical CPUs and GPUs in the control room, as well as the more advanced supercomputers and high-performance computers. But those computing technologies, by their nature, will rely on bits to encode information. A bit can be at 0 or 1 at a time. Then with multiple bits, we can encode complicated information, but still one state at a time. So this potentially means that we might have limited speed for handling very large systems, and we may only be able to handle one task at a time. Therefore, as the system scale is approaching new level, those classical computing technologies may also approach their limit. This motivates us to think about what if we could have multiple states at the same time. And this is exactly what makes quantum computing so exciting, because the qubits could really do this. They can be at 1 and 0 at the same time with a certain probability, which is called superposition. Therefore, with multiple qubits, we can really represent multiple states simultaneously and potentially handle large scales and multiple tasks at the same time. This really leads to the quantum speed up for a range of problems over the classical computing, and especially when your problem size is very large. Therefore, our vision here is actually to work on the quantum-based grid analytics. Ever since 2019, we have actually been working on applying quantum algorithms to power system analytics. We have developed the world's first series of quantum algorithms for power system simulation and optimization. But that is actually not the end of the story, because during this journey, we are really seeing that many of the standard quantum algorithms work well for the toy problem, but not the real problem. So there are many challenges we are facing when applying the quantum computing technologies to real problems. And in this project, we will be specifically looking at how can we make the quantum computing more capable and usable for real problems. So we are particularly interested in two knowledge gaps. One is that how can we map between the classical model and the quantum model? So just like the cuneiform doesn't really directly talk to the smartphone by their nature in the same language, the quantum space actually doesn't talk to the classical space directly. So this potentially means that we need to encode our classically formulated power grid models into the quantum model, and then after calculation, decode them back into our classical space so that we can have useful information for grid operations. But unfortunately, until today, there is no standard template to do such conversion efficiently with manageable complexity. And the second challenge is really how to have practical benefit for using quantum for real-scale grid analytics. As we have mentioned, quantum really has very promising speed up, But most of those speedups are actually in theory or for toy problems, not for the real problem. So this is actually a dilemma not only in the power and energy society, but actually for most of the engineering problems. So in this project, actually, we will be trying to look at this problem in a totally different way. That is, rather than applying quantum for engineering problems, we will try to see how we can synergize our understanding of the physics knowledge of engineering problems to design domain-specific quantum algorithm. So we call them the great inspired quantum algorithm. Through such a process, such a synergy, we envision to achieve more higher performance computing capabilities, such as being more scalable, being more resilient to the quantum noise, or requiring less quantum resources. Okay, I will share 2 examples to show why we believe this grid-informed algorithm will perform better than the general-purpose quantum algorithm. Let us consider a simplest power grid with nodes and branches here and see how we can encode them into quantum space. So the general way might be we establish the classical model of this power grid by the matrix and vector, and then we encode them into quantum operators. So such a process will probably require a very complicated decomposition process to decompose those matrices into quantum. But what we will be doing here is actually to take advantage of the topology information of the known power grid. We can use very simple quantum operators to represent each device of the power system. Then with the known topology information of the whole grid, actually we can do a very simple linear superposition to connect those different quantum operators together to directly represent our power grid. Sorry about that. Yeah, so through such a way, actually we can directly formulate our power system but without doing any decomposition. And then let's think about in this power grid, now we further have the injections, current injections into the system, and this will produce bus voltages. Then how can we get those bus voltages from the quantum algorithms? Okay, a standard way is actually we get the probability from quantum circuits, from the quantum operators. But for real-world power system operation, those probabilities actually didn't provide much useful information because we really need the exact values of the voltages, whether they are positive or negative, what is the number of those, rather than the probabilities. So what we will do is to take advantage of another information that is the parameters of the power system, which indicate that we can directly know whether the voltage is positive or negative by just looking at the signs of the currents. So this will really enable us to directly get the exact value from the probability information, which will be usable for the system operations. Okay, so in this project, we will actually explore different types of the physics knowledge of the power system, like topology, parameters we have mentioned, as well as the symmetry and dynamics and more information to make quantum computers can directly and scalably handle that very large power systems with millions of devices. Meanwhile, we will also be looking at the different events, different tasks, to explore their information about the similarity and dependency between different events so that we can use quantum to efficiently handle those different events at the same time. Through such a process, we will establish a more practical framework to scalably and efficiently handle those power systems by using our physics knowledge. And our ultimate goal is actually to achieve a super polynomial speedup, but with just using a moderate number of qubits. To provide an estimation, actually using such a framework, we will be able to handle power systems with millions of nodes and under thousands of events by just using tens of qubits here. So we believe such a perspective, such a vision of synergizing the physics knowledge with quantum will actually provide a more deployable quantum solution for the real scale grid applications. And more importantly, beyond the power and energy society, we also believe that such a mindset will actually provide insights for developing more domain-specific quantum solutions to connect our well-established physics knowledge with those emerging quantum solutions to solve more broader engineering challenges. Okay, so that's all I want to share here. Thank you for your listening, and I'm happy to take questions.
You did a nice job of motivating why we get driven toward quantum computing needed for the power grid system. What you didn't do very much in this presentation, and I found only one little piece in your write-up, which is kind of where your own project fits in. I mean, I'm convinced that quantum computing, if it works, will be valuable for the grid. That part I understand. You have a little section where but when we talk about your work specifically and where it fits in this big system of a lot of people in a lot of places worrying about this general problem, you have a little section called risks and feasibility, which I thought was maybe your own work, or what is your piece, or that's separate and identifiable and it's larger?
Yeah, actually we will be specifically looking at two types of computing challenges in the power system. One is the simulation and one is the optimization. Actually, they really represents two critical aspects for power system computing. One is, how to solve the linear or nonlinear equations in system, and then one is how to optimize either the system behavior or the control perspective. So in both directions, actually, we will see how we can fit the physics knowledge into our design for this simulation or optimization algorithms here. And this is actually what I covered in the proposal, but I didn't really go into the details in this presentation. Yeah, but that is the high-level idea here.
Thank you. I think that was also a part of my question, but I also maybe like you to expand on it a bit more.
Sure.
Just with, as you know, with quantum computing, obviously, companies like IBM, they are looking to see what's the quantum advantage as it applies to many of these problems, and grid is one of those major problems. With the work that Oak Ridge is doing and NREL is doing and all of that, where do you see your work complementing what they do?
Yeah, thank you. That's a valid point. So basically, what we see is that most of the work on the quantum computing is actually focusing on the quantum algorithms themselves, rather than how can we really convert our classical problem into quantum and then perform calculation for this specific problem, and then convert our result back into the classical space. So what we are trying to solve and what we are trying to claim in this proposal is that actually every step in this whole pipeline will really impact the algorithm performance rather than only focusing on the quantum algorithm itself. And to do this whole pipeline, it is really problem specific. It depends on what type of problem we are looking at and what type of system we are looking at. That is actually exactly the reason why we propose to encode the physics knowledge into different steps of this whole pipeline, so that we can, get the benefit, the speed up for this whole framework, rather than only have speed ups in the quantum space. Because the speed up in the quantum space doesn't really mean that we can have the whole speed up for this whole engineering problem. Yeah, that is how we see our work is actually complementary to the general quantum work that is done either by the quantum experts or the computer science experts here. Yeah.
Okay, nice presentation. Thank you. If I understand correctly, your work is basically, as you just said, encoding the physics knowledge of the grid into the quantum space. So that is the development of basically quantizing the grid, so the development of the unitary operators in the Hilbert space. So how do you know that you have a complete set of operators and you haven't missed something? You haven't missed a particular important piece of the physics when you quantize the grid?
Do you mean when we do the mapping, how to
when you do the mapping, how do you know that you've included everything that you need to include?
Yeah, Thank you for that. Yeah, basically what we are looking at here is that, say we have an accurate power system model, and then we actually will be kind of like also looking at the quantum representation for that. And this mapping by their nature is to decompose the matrix into their either linear combination of the unitaries or other types of unitary operators. So there will definitely be inaccuracy here, but what we are trying to do is to achieve a certain level of accuracy which is actually guaranteed by the formulation of each device. And then if each device is actually accurate enough, when we connect them together, they will still provide a certain level of guarantee for the whole system behavior. But I'm not sure whether this is exactly what we are asking for.
Yeah, that's good enough. I have a follow-up.
Sure.
Then the accuracy, how do you define or compute the accuracy of your quantization of the grid?
Oh yeah, thank you for this question. Yeah, so basically for the whole picture, actually we'll be definitely comparing the behavior with the classical computing. But within the quantum algorithm themselves, but because the nature of the quantum computing, they are kind of like more probabilistic, so they will definitely have errors inside that. This will probably require us to do an outer loop error correction in this whole process to ensure the accuracy here. Thank you. Okay. Oh, thank you.
Thank you, Ifan. Let's have another round of applause for three brilliant young scientists. All of them are a testament to the culture of bold discovery at Stony Brook University. Their dedication and hard work are the foundation of this research institution, and we are immensely proud of them and all who work with them. This concludes the formal portion of our program. I invite our audience to please join me for a reception outside, not outside the building, but outside the hall, while our judges deliberate to select this year's Discovery Prize recipient. We'll reconvene in about 30 minutes to reveal the winner. Thank you very much. Just feel it there and hear what a center of science Stony Brook University is. I could not be prouder of our young colleagues or more appreciative for those who have done the judging. So this is the moment we've all been waiting for. It's my distinct honor to announce the winner of the 2025 Discovery Prize, Dr. Jennifer Cano.
Thank you, everyone. Thank you, everyone, for coming and for judging. I want to give a special thanks to Nancy and Radha, who really helped me prepare the talk. A special thanks to my research group, who came out today to support me and who've been really fun to work with and inspire a lot of these ideas. And then also a thanks to my family, who's been supporting me throughout this whole process. So thanks to everyone for coming out today.
So Jennifer, congratulations again. We're going to do some photos afterwards, but I want to say how proud we are of you as well as of your colleagues. Stony Brook's future and the world's future lies in knowledge, discovery, and creativity, and in high risk and high reward ventures that are so boldly undertaken by Jennifer, and also by Paolo, and also by Ifan. Thanks to all of you. Thank you for your curiosity, your continued brilliance, your willingness to push boundaries, your pursuit of compelling questions, and for pushing yourselves and your fields to new limits. Thanks to our judges. We are so lucky to have enticed three amazingly accomplished senior scientists, all brilliant to hear this afternoon. and I am so appreciative to you. Finally, thanks to all of you for joining us for this celebration, for indicating by your presence that you believe in discovery, that you believe in science, that you believe in young scientists, and that you're committed to our institutions remaining a center of scientific excellence. So thank you for being here. It says a lot. It says a lot to those who competed today, and it says a lot to the whole university. We care about this stuff. Thank you very much. Have a wonderful evening.